Welcome to another video lecture. This one will be once again on electric potential energy and electric potential and what the actual definitions and meanings are. We're going to go through this kind of the same analogies that we did last night, but it's going to put them down in a little bit more of a concrete way. So follow along in your textbooks, sections 19.1 and 19.2, and please make sure to answer the questions at the end. Here we go. The electrostatic force is a conservative force, and if we think back to what we did in the fall, a conservative force is something that is independent of the path that it takes to travel between 2 points. So this just means that whether you're moving a charge from far away to close to another charge, it doesn't matter whether you zigzag back and forth. All it really matters is the displacement between the 2 points. So the work done depends on the force applied and the displacement between from where you've moved it, in this case the electric force. And this causes a change in electric potential energy. Once again, potential energy is just stored energy due to position. So when we talked about gravitational potential energy, it was the energy of some object with mass due to its position relative to another object with mass. And so we always compare that to like the surface of the Earth. With charges and electric potential energy, it's the potential energy of some charged object due to its position within an electric field. Now, so we're going to talk about this idea of gravity and this electric force here and compare them back and forth. So the idea that weight is kind of the equivalent to the electrostatic force. And when you do work on some object with mass, you pick it up, you move it some distance, and you change its potential energy. You also need to, the equivalency there is doing work to move a charge. So you need to move a charge from one position to another. And we'll see how that differs depending on the direction that you move it in a little bit. So we have potential energy, gravitational potential energy, and we have electric potential energy. The acceleration due to gravity is the equivalent of the strength of the electric field at that point. And the other thing that we're going to come in and we're going to start talking about is this voltage, which depends on it's a difference in electric potential. So it's the difference in potential between 2 points. We'll talk about that more in just a second. But the idea here that this idea the potential energy is still the same idea. It's due to position, and there's if you understand the idea that objects with mass have a gravitational potential energy around the Earth, charges or objects with charge within an electric field will have some amount of electric potential energy similarly. Electric potential depends on the amount of potential energy for some test charge at some point within a field. The electric potential energy is commonly defined as the energy per charge. So it's the amount of electric potential energy divided by the charge itself. It's measured the electric potential is measured in volts. And when we talk about voltage, we're talking about the electric potential difference between 2 places. So we're going to come back to that in a little bit later when we start talking about circuits, but the electric potential is often sometimes referred to as voltage, but that's kind of like an incorrect thing. It's just the energy per charge at some point. One of the things about electric potential energy and electric potential is that we can't determine them and say that forever this point here will have such and such a potential energy or something, or a potential, electric potential. It's that it's relative, it's due to position. I mean, potential energy is due to position, which is relative to other objects that can move or change. So just like potential energy, or gravitational potential energy, is due to the height of some object. And if you think about it, we could say the height of a book held over a table. Or you could say, well, that height could be over the floor. Or we could say, well, let's look at the whole system and say, what is the total potential energy of the book relative to the ground outside? So it depends on position. So it's all relative. Just like electric potential energy, it depends on, well, we're going to look at these two small charges in this area. Well, what about other charges? What about other things going around outside of it? Now, we'll look in kind of idealized cases in this class, so we won't have to worry about some of that stuff. But just understand that there's no finite or absolute way to measure potential energy or electric potential energy or electric potential. One of the analogies that I'm going to make several times is that we can say that the electric potential is similar to a topography map. Now, a topography map graphs a three-dimensional area around some surface or whatever, and it shows the height of a mountain or something, or a valley, for example. Electric potential is similar in that there is a higher potential energy closer to some charge, in that it takes more work to get that charge there. And this is talking about two positive charges, and you have one positive charge, and we always refer to as a test charge generally as a positive test charge. And so it takes a lot of energy to get that other test charge really close to that other positive charge, because they want to repel each other due to this electric force. And so a positive charge will want to move from an area of high potential energy to a lower potential. So it will accelerate away from a positive and towards a negative. So you think of positive charges as these big hills, and a negative charge as these big valleys or holes or whatever you want to look at them. And we'll see more of this tomorrow in the next night. But they are these two parts, and a positive charge will want to follow along, similar to gravity or something else like that. Will fall down the hill and into the hole, whereas a negative charge goes in the opposite direction. So, and we'll look at that. And one last thing is just we measure this energy of a single electron. We measure this in units of electron volts. And we'll talk about that more later on, but just kind of might as well introduce it right now and then keep moving on, and we'll come back to it. All right, a couple of quick questions, and you may need to use the video from last night, the one of me actually lecturing by the board, to actually go through this. First, I want you to define three vocabulary words, so electric potential energy, electric potential, and voltage. So define each one of those, please. Second, when two charges are moved next to each other, we cannot simply just calculate the electric potential energy by multiplying the force at this new point by the displacement moved of the two charges. And I want you to tell me why this is. So think about you have 1 point charge, and you bring in some other charge from infinity, and you bring it in closer. What's changing as you bring it in? So think about those ideas there. And a couple quick sentences to answer that one. All right. Thank you very much. See you tomorrow in class, and bring questions with you, because I understand that this may be a difficult topic, but bring questions with you. Thank you very much.